Hi, Tracy. Okay, fine. No issues. Yeah, fine. Dhananjay won't be attending today's class. We have learned about these types of hybridization, right? Formation of molecule means like we are supposed to start. Fine. Okay, now see in this formation of molecular orbital, what is given? It's a linear combination of atomic orbital. So in a linear combination, in short form, we called it as a LCAO. It's abbreviation for it, linear combination of atomic orbitals. What is given in this check? The formation of molecular orbital can be explained by the linear combination of atomic orbitals. Combination takes place either addition or by subtraction of wave function as shown below. Means either wave function would be add or wave function would be subtract. Okay. So whenever you draw any sort of diagram, this formation of molecular orbital, you have to draw the energy graph. So always keep it in your mind, energy would be go higher at the upstairs. Means like when you draw the, like this heading arrow shows the energy. Means when you move top to bottom, sorry, top to bottom, your energy, molecular orbital energy would be decreases, right? And here you have to show the mediator. It can be bifurcate the energy, right? So energy below this line would be less, energy above this line would be more. These things you need to keep it in your mind. Now, what do you mean by BMO and ABMO? So this is bonding molecular orbital. Okay, and these are anti-bonding molecular orbital. Okay. Now, energy of bonding molecular orbital is always less as compared to anti-bonding molecular orbital. Its energy is more, right? Bonding molecular orbital will be shown by the psi p. Sorry, and anti-bonding would be shown by psi a. Okay, and these are nothing but the average energy. Here would be the psi 1 for the first molecule and psi 2 for the another molecule. When your two atoms are combined to form a molecule, that time energy of the molecule is nothing, energy of the first atom is psi 1, energy of the another molecule will be psi 2. When psi 1 and psi 2 combine, it will form bonding molecular psi b and anti-bonding molecular orbital psi a. These things you need to keep it in your mind. Understood? Psi 1 would be what? These are the molecular orbitals for psi 1 atom. Right. Psi 2 is what? It's a molecular orbital for psi 2 atom. Psi 1 and psi 2 atoms, molecular orbital mix, hybridize with each other to form a two section. One is the bonding molecular orbital, another is the anti-bonding molecular orbital. Among that, bonding molecular orbital has a less energy and anti-bonding molecular orbital has a more energy, right? And the bonding molecular orbital would be shown by psi b and anti-bonding would be shown by psi a. Fine. Clear? Yes, Shreyasi? This diagram you understood or not? Fine. We'll move forward now. Clear? Shall I erase it? Now next. Now see what is given over here. The molecular orbital formed by the addition of atomic orbitals is called bonding molecular orbital, while molecular orbital formed by subtraction of atomic orbital are called as anti-bonding molecular orbital. Understanding? If it is formed by addition, right, then it is bonding molecular orbital. Bonding molecular orbital would be formed by what? Addition of atomic orbital. It is formed by what? Addition of atomic orbital. And when it is formed by the subtraction of atomic orbital, that time it is called as anti-bonding molecular orbital. So this is BMO and this is ABMO. Okay. Condition for the combination of atomic orbital, when it will be get combined, when addition occur, when subtraction occur, that also we need to see, and what essential conditions are there for that, that too we have to see. The first thing which is given to you, that the combining atomic orbital must have almost equal energy. So those are going to combine, those are going to add with each other. They must have what? Equal energy, the first condition. Second condition, the combining atomic orbital must have same symmetry about the molecular axis. Because if the molecular axis, they have a same symmetry, then only they can combine with each other, isn't it? This we have already seen. These are the p orbitals, axis of symmetry. These are the p orbital axis of symmetry. Then only overlap would be possible in this way, correct? Yes or no? In this way, addition of the orbital would take place. Fine. The combining atomic orbital must overlap to the maximum extent. So those are combined with each other. That orbital must be overlapped in a maximum extent. Right? Maximum extent means what? Maximum extent means what? So there would be more and more strong bond in between by the axial overlapping. And then maximum overlap happened. When maximum overlap happened, then only bond become more stronger. Now they have given you types of molecular orbital. Which types of molecular orbital would form? Right. Atomic orbitals already we have seen. Now, which type of molecular orbital would be formed? That we have to see. Sigma molecular orbitals are formed, and even the pi molecular orbitals are also formed. Just we have seen the sigma bond and pi bond. In the same way, we have two different types of molecular orbitals. In that, first one is sigma molecular orbital and second is pi molecular orbital. So sigma molecular orbitals are formed by what? They are symmetrical around the bond axis. How they will be? They are symmetrical around the bond axis in the same way how I am explaining here. In this way, they are symmetrical, right? But then pi bond, they are not symmetrical because pi bond is formed by what? By the lateral overlapping. Already we have seen, correct? Sigma bond is formed by what? Sigma bond is formed by axial overlapping, right? And pi bond is formed by lateral overlapping. Isn't it? And because of that, we can say sigma molecular orbital are symmetrical in nature and pi molecular orbital are non-symmetrical in nature. Correct? Because of the presence of positive lobes above the negative lobes below the molecular plane. Understanding? Because in the pi bond, positive lobes are present below the negative lobe. In this way, it would be. Right? And when it get laterally overlapped, then only pi bond would be formed. And hence we said that pi bond is weaker as compared to sigma bond, because sigma bond is formed due to axial overlapping and pi bond is formed due to what? Lateral overlapping. Then the next one, electronic configuration and molecular behavior that we have to see. Shall I erase it or you are noting down? Are you noting these things? No. Noted? Okay, fine. I'll erase. No issues. Now check it now. The thing which I wanted to explain you about electronic configuration and molecular behavior. what is given about the electronic configuration and molecular behavior. The distribution of electrons among the various molecular orbitals are called electronic configuration of molecule. Distribution of electrons among the various molecular orbitals is called electronic configuration, right, of the molecules. And stability is also given. Stability of molecule is what? If NB and Na. NB matlab, what do you mean by NB? Number of electrons occupying bonding orbitals. Na, number of electrons occupying into anti-bonding orbitals. Then you have to keep it in your mind. If NB is greater than Na, molecule will be stable. And if NB is less than Na, then molecule will be unstable or maybe in excited state. Okay. Bonding molecular orbital has more electron than that of the anti-bonding molecular orbital, then that molecular will be stable. And if bonding molecular orbitals have a less number of electrons as compared to anti-bonding molecular orbital, then it will be unstable. These are the basic concepts you should be aware of. Now see the next. Bond order. How to calculate bond order already we have checked. Isn't it? Have we checked it earlier or not? Bond order? Yeah. You were there when I explained about the bond order? So what do you mean by bond order? How are you supposed to calculate? It would be bond order is equal to 1/2 your number of electrons present into the bonding orbital minus number of electrons present into the anti-bonding orbital. That is nothing but the number of bonds present in between two atoms. Correct? We have seen already about it. Now, this is a formula, but then here you don't have to see the bond because bond won't be shown to you. What would be given to you? You may have a number of atomic electronic configuration would be with you. With the help of that, you have to show the hybridization. With hybridization, you have to make the overlap of the orbitals. Molecular orbitals you have to draw, like how we have to draw that energy graph. Then you have to fill the number of electron into the bonding and the non-bonding molecular orbitals. How many electrons are there into the bonding orbital? How many electrons into the anti-bonding orbital? That you need to count, right? And then you can calculate the bond order by using this formula. Please note down this formula, it's essential. The bond order may be whole number, it can be fraction, and even it can be zero. It may be positive or negative. So don't get afraid if you get some of the other way. Okay? Like suppose if you get a negative or if you get the positive value, don't be afraid. Any value you will get. Fine. Okay. Now, nature of bond, how you will come to know? Integral bond order value for the single, double, triple bond will be 1, 2, 3 respectively. So you will come to know bond would be single bond, double bond or triple bond. Now bond length, the order is inversely proportional to the bond length. Bond order is inversely proportional to bond length. Greater is the bond order, smaller will be the bond length. Means multiplicity will decrease the bond length. Multiplicity of the bonding will decrease the bond length. If there would be the single bond, it is longer as compared to double bond, and double bond is longer as compared to triple bond. These things you need to keep it in your mind. Now, what about the magnetic nature? Magnetic nature is dependent upon if all the molecular orbitals have paired electrons, the substance is diamagnetic. And if more molecular orbitals have unpaired electrons, it is paramagnetic. Example is given O2 molecule that we will see. Suppose you get the bonding orbital, these are the bonding orbital, and in that number of electrons all are paired, spin and paired. Then it is what? Diamagnetic. How it will be? It will be diamagnetic. And if most of are single, only one electron is present into the molecular orbital, then it is paramagnetic. So this is about the magnetic nature or magnetism. Okay. Bonding in some homonuclear diatomic molecules, we have to check. So whatever basic things you have learned now, it's like how to calculate bond order, like what is bonding molecular orbital, anti-bonding molecular orbital, how we have to frame the molecular orbitals from the atomic orbital, and then how to fill the electrons, how to calculate the bond order, bond length, and even the find out the magnetic nature. That all things we are going to see in detail for the below examples. First one, homoatomic molecules we are going to see. Yeah, fine. Yeah. Now we know that about hydrogen molecule, it will be formed by two hydrogen atoms, correct? H2. If I have to form here H2, it will be formed by what? Two hydrogen atoms. Hydrogen combine with each other to form H2 molecule, correct? So what is the electronic configuration for one hydrogen? That is 1s1. Here also 1s1. So they have taken here the hydrogen molecule H2. It is formed by the combination of two hydrogen atoms. Each hydrogen atom has one electron in its 1s orbital. Just now we have seen 1s1, 1s. So the electronic configuration of hydrogen molecule would be what? Now you can check here. For first hydrogen, it will be 1s. Another hydrogen has a 1s. Okay. It is, they have written H2 plus, means another hydrogen does not have any electron over here. Are they shown any electron? No, it is H2 plus, and only one hydrogen has the electron. So this is the H2 plus molecule. In that, it will give you two bonds, two molecular orbital. One is a sigma, another is a sigma star. This is what? Bonding molecular orbital. This is anti-bonding molecular orbital. Right? Anti-bonding molecular orbital. So it has a 1s electron. This 1s also has one electron if it will be H2 molecule, but then it is not a H2 molecule. What it is? H2 plus. Correct. So that's why here they haven't shown any electron. But then if you want to show it for the hydrogen molecule, how it will be, I'll show you. Shall I show you for the H2 first? Then only we plus and minus charge will take. See. Okay. Now if we have to see the H2 molecule, this plus charge you forget what. Now 1s has a 1 electron, one hydrogen has 1s1 electronic configuration. So 1s has 1 electron. Another, this is also hydrogen atom. It also has what? 1 electron inside it. Fine. Now what happened? One electron would be here, one electron would be here in a molecular state. Another electron goes here. So H2 molecular has an electronic configuration what? H2 molecule. H2 molecule, its electron configuration is sigma. How many electrons are there? 2. Understanding? This will be the electronic configuration for H2 molecule. Understand? Sigma molecular orbital has how many electrons over here? 2. Because one molecular orbital has a capacity to hold how many electrons inside it? 2. Keep it in your mind. Okay? Fine. Now the next step is what? They have removed one electron from one of the hydrogen and it become what? It become what? H plus ion. H2 plus ion, not H plus ion, it will be H2 plus ion. It has two atoms, but then one of the atom hydrogen doesn't contain any sort of electron inside it because it's a H plus ion. So your one hydrogen has the electron, another hydrogen doesn't have the electron. Only one electron would be into the sigma. So H2 plus has the electronic configuration would be what? Sigma 1, correct? And when it will be H2 minus, that time what? It has one electron, one hydrogen atom. It has a one electron into the 1s, correct? H minus has two electrons, right? Minus means one electron has been added. Normally it has one electron, and as it is minus charge, one more electron has been added. So here would be the 2 electron due to minus charge. So what happened? one electron from here, one electron from here would be completed your bonding molecular orbital, right? And whatever would be remain extra, that would be jump into the excited state anti-bonding molecular orbital. So electronic configuration for H2 minus is nothing but sigma 2 electrons and sigma star how many? 1 electron. So this would be your electronic configuration. Keep it in your mind. Understood? And the next one, if you see the helium atom is completely, it has a completely filled s orbital. So 1s has a 2 electrons inside it, 1s2, 1s2. Correct? Here are the 2 electrons, here are the 2 electrons. And when He2 molecule would form, 2 electron would go into the sigma and 2 electron would go into the sigma star. So this is bonding molecular orbital and this is anti-bonding molecular orbital. And its electronic configuration for the He2 molecule would be sigma has 2 electron and sigma star also has a 2 electron. Clear? Yes? Understood these diagrams or not? Fine. Now see, this indicate that two hydrogen atoms are bonded by single covalent bond. Bond dissociation energy of hydrogen has been found 438 kilojoule per mole. What is the bond dissociation energy for hydrogen? 438 kilojoule per mole. And bond length is 74 picometer. No unpaired electron is present. Therefore, H2 molecule is normally H2 molecule is diamagnetic. Right? Yes. Why no unpaired electron? Because we have seen whenever it will be one electron over here, it goes and pair up this sigma bonding molecular orbital for the H2. Okay. Yes or no? So there won't be any unpaired electron. These are the paired electron. And hence the nature of hydrogen is diamagnetic. Now helium molecule, if you see, each helium atom contains 2 electrons. Thus helium molecule, there would be 4 electrons. An electron will be accommodated in sigma 1s and sigma star 1s molecular orbital. Here 2 and here 2. These are also paired electron and hence He2 molecule is also diamagnetic. It is also not paramagnetic. But then He2 plus, sorry, hydrogen plus ion and hydrogen minus ion molecule would have a unpaired electron and hence it would be paramagnetic. Clear? Yes or no? You can see He2, it has one He2 plus and one unpaired electron. He2 minus, it has one unpaired electron and hence these are paramagnetic in nature. Clear? Yes? Fine. Now we'll move down. We have to check the electronic configuration. Yeah. Check it here, electronic configuration, He2, 1s sigma 1s2, sigma star 1s2. Correct? And bond order would be 1/2, 2 minus 2, that would be 0. 2 minus 2 is 0 because in sigma 1s2, how many electrons were there? 2. Sigma star 1s2, how many electrons were there? 2. So 1/2 into 0 is equal to 0. He molecule is therefore unstable and does not exist. The bond order can be 0. Now for the lithium molecule, if we see, its electronic configuration would be what? Just give me a while. Just give me a while, okay? Yeah. Hello. Am I audible, beta? Am I audible? Fine. Now see, lithium molecule. We know that one lithium, it has number of electrons two. Sorry, three. Atomic number is three. Number of electrons are three. So its electronic configuration would be 1s2, 2s1. Correct? So there are how many electrons for the two lithium to the lithium molecule? Means lithium attached to lithium, it will be from lithium molecule, right? Fine. So because of that, what one lithium has three electrons, so two lithium atoms must be having six electrons. So electronic configuration, if I have to write, we know that there would be how many electronic what would be the electronic configuration? In the same way, if we have written over here, we have to feel what these electrons. Your lithium this side, another lithium this side. Its electronic configuration will be what? 1s2, 2s1. 1s2, 2s1, right? And this would be form bonding and anti-bonding molecular orbital. Here it will be bonding and here it will be anti-bonding, correct? Yes or no? So in bonding, there would be what? 1, 2, 3, 4. Correct? This is what sigma 1s2, right? Sigma 2s2, then sigma 1s2 and sigma star 2s2. Not in that manner, it will be arranged in that way. I'll let you know. Can't explain in this way, it will be confusing. Here is a lithium, here is a lithium, correct? Its molecular orbital would be what? It consists 1s2 and here it will be what? 2s2. 2s1, sorry. Here is 1s2 and here 2s1. It's an electronic configuration for lithium, right? Yes. So one molecular orbital would be formed here, another would be below this. Correct? Which has a less energy? This 1s2 has a less energy, right? So sigma 1s1, sorry, not 2, 1s and 2s. Sigma 1s, then here sigma 2s. These are the bonding orbital, bonding molecular orbital. If you go up, there again you will get the anti-bonding molecular orbital. This would be again sigma star 1s, and here upside it will be what? Sigma star 2s molecular orbital, right? So from here, how many electrons would be goes into the 1s? 1s2, so that will be going to sigma 1s2. Then again here 1s2, it will be goes into sigma 2s, correct? Now here one electron and here is also one electron. It will be goes into what? Sigma star 1s. And this your sigma star 2s would be remain vacant. There won't be electron. So your electronic configuration would be what? See, check it here. Sigma 1s2, you are able to see here. Sigma 1s, how many electrons? 2 electrons, correct? Then sigma star 1s2 is here, right? Yes. And then see, you are able to see sigma 2s has how many electrons? 2 electrons, right? Yes or no? Sure. Sorry. Sigma 2s has how many electrons? 2 electrons. So your electronic configuration would be sigma 1s2, sigma star 1s2, and sigma 2s2. Understood or not? Tracy, are you there with me or shall I explain it again? Because this understanding is very important. Okay, fine. Understand sigma 1s2, sigma star 1s2, and sigma 2s2. These are the electrons. Among that, how many are bonding? You can check. Sigma 1s2 is a bonding and sigma 2s2 is also bonding. So your NB is nothing but 4 and NA is equal to how many? 2. Correct. Now bond order, how you're going to calculate? 1/2 into NB minus NA. That is equal to 1/2 in bracket 4 minus 2, which is equal to 1/2 into 2. 2 1 are 2, 2 1 are 2. Bond order is 1. So as we know that in this, all are paired electron, 2 electron, 2 electron, 2 electron. There is no single electron, and hence its magnetic property is diamagnetic. If there would be unpaired electron, that time we could say it is paramagnetic. But then here is a diamagnetic magnetism shown by the lithium molecule because all electrons are paired. Since molecular orbitals are completely filled. Clear? Yes? Understood about the lithium molecule? So those things you need to keep it in your mind. Let me erase it. If you want, you can click the picture for it. Shall I clear? Here is it. Right. Oh, you said 1 minute. Note it down. Once you have done, text me so I can scroll it down. Yeah, fine. Yeah. Now you're going to see. They have given here some. This part is given over here. It won't be understanding you right now. I'll explain you thoroughly. Okay. In the same way we have to do, but then this is the energy levels. When which has more energy, which has a less energy. These are two things very important that you need to keep it in your mind with respect to oxygen, fluorine, neon, then boron, carbon, and nitrogen. So this is the energy sequence. If you take a picture of it, that would be helpful for you. I'll explain you later. Take a picture of it. Okay. Now hydrogen bonding is one of the important factor that we are going to see what it is. Yeah, only hydrogen bonding pointers remain. So tomorrow we will see few more molecular orbital formation for the rest all molecules like oxygen, fluorine, etc. And that we will check. Then I'll explain you how mistake you have to find out the bond order and magnetic character of few other important things. Where my cursor went? Why? Oh, okay. When highly electronegative element like the nitrogen, oxygen, fluorine are attached to the hydrogen to form a covalent bond, the electrons of the covalent bond are shifted towards the more electronegative atom. This we have learned into the dipole moment and even the polar molecules. Thus, partially positive charge develops on the hydrogen atom, which forms the bond with the other electronegative atom. This bond is known as hydrogen bond, and it is weaker than that of the covalent bond. For example, HF molecule, hydrogen bond exists between hydrogen atom and one more of the fluorine atom of another molecule. Here, it can be depicted as, suppose you have a HF molecule in your hydrogen fluoride has been formed and you have taken the liquid of it. So we know that this bond is, it has a dipole moment, it's a polar bond. So there will be the positive delta on the hydrogen and negative delta charge on the fluorine. What we know, in its near vicinity, there would be again another hydrogen and another fluorine would be there, right? As a molecule, HF molecule. But then here also positive charge would be there on the hydrogen and negative charge would be there on the fluorine. So what happened when this electronegative fluorine and electropositive hydrogen come into the close proximity, it will form bond between them. It may have a force of attraction due to opposite charge generated on their head, negative delta and positive delta. So due to this sort of attraction, it will form a bond, and that is called as what? Hydrogen bond. You can see one bond is being shown by the solid line and another would be by dotted line. So this dotted line bond is nothing but what? Your hydrogen. Keep it in your mind. Hydrogen bond is always shown by what? Dotted lines. So they have said hydrogen bond is of two different types. One is intermolecular hydrogen bond and another one is the intramolecular hydrogen. Now, what is the basic difference in between? Intermolecular hydrogen bond means it is formed between two different molecules of a same or different compound. For example, HF molecule, water molecule, etc. What does it mean? It is formed between two different molecules of the same or different compounds. Suppose here is a HF and even the H2O, H, and O. So that time also, suppose this HF would be here and this hydrogen also would form the hydrogen bond with oxygen. It can form because due to positive charge and oxygen has a negative charge. So this is also sort of hydrogen bond. Okay. So it is forming between what? Two or more molecules. That would be of same or different molecules, right? And these are intermolecular hydrogen bond. Now, intramolecular hydrogen bond means within that molecule itself. See, in this time, hydrogen atom is in between the two highly electronegative fluorine, nitrogen, oxygen atom present within the same molecule. For example, in the nitrophenol, orthonitrophenol, the hydrogen is in between two oxygen atoms. Correct? Yes or no? Orthonitrophenol, hydrogen would be in between. Where it will be? Orthonitrophenol. Come on, tell me. What is the structure of orthonitrophenol? This would be, suppose your benzene. Okay. This is phenol, means it will be OH. Right. Nitro group means nitrogen, double bond O. And here O minus. Wait. Here it will be O minus. Now it is electronegative, it is electropositive, and there would be the bond in between, right? So it is happened within the molecule itself, hydrogen atom in between two electronegative atom. Either you can take this oxygen or even you can consider nitrogen. Instead of oxygen, you can connect it with the nitrogen as well, because nitrogen is also electronegative and oxygen is also electronegative. So it will be form a hydrogen bonding, and because of that, it is very difficult to lose this hydrogen atom due to hydrogen bonding. It will take, it's require a lot of energy, right? Yeah. So it happened within the molecule itself. There won't be two or more different molecules. There would be only one molecule, and within that molecule itself, hydrogen bonding will be takes place. Okay. Now see what is given. 10 kilocalorie per mole energy would be required to break this HF bond. Here 7 kilocalorie for the HO, and here 2 kilocalorie energy is required to break hydrogen and nitrogen bond. Okay, that's it. So tomorrow we will see only few more like this sequence. I'll explain this sequence, and we will see the this one, molecular structures, bonding and debonding thoroughly. 2-3 diagrams would be there, especially for the nitrogen, fluorine, then carbon monoxide and oxygen molecule also we are going to see. Okay, and this sequence I'll explain to you. And I hope your chapter would be complete tomorrow. Right? This part only I have to explain tomorrow. That's it. So shall I end the class? Yeah? Yeah? Yeah. Bye. Take care, beta.